word. And we hope that also with the 7 universities, we are open for collaboration, exchange of staff, exchange at doctoral level, exchange at student level, whatever. Your dean is an expert in mathematics and informatics and science. Then you know that in signal processing, we can differentiate signals. And if you differentiate signals, you simply increase the noise. We all know that. If we integrate signals, we come to something more smooth, something more coherent, something more nice. That's my wish for the whole network in presence of an expert in signal processing, mathematics, and so on. That you all, that with our help, we try to be part of that as well, that we become integrators, not for the better ranking, not for the better papers, but to provide food to everybody who needs it. Thank you very much.
Thank you, Professor. The next, we are pleased to remarks from the Associate Professor Dr. Supandi, SSE, MSE, as the Dean of Faculty of Mathematics, Natural Science, and Information Technology Education, on behalf of the President of our university, to give an opening remarks of this agenda. Dear Dr. Supandi, the floor is yours.
Terima kasih. Thank you so much. Good afternoon, everybody. Honorable Ravian Vanipen from KU Leuven Delegates and Dr. Monica Polanska and Dr. Sakja Bonsale is meant as guest speaker. Thank you so much. And from University College Dublin, Dr. Rajat Naik, Prof. Alcino Bernardo Moraes and Prof. Ruiz Moraes from Universitas Catholic Portuguese. Thank you so much for coming. And then Prof. Ian Chis from Alsace University of Applied. Thank you so much. Pak Dr. Yoga, terima kasih dari Undip ini. Thank you so much, Prof. Pak Dr. Yoga. Director of International Head of the Affair Office Universitas PGRI Semarang, Dr. Thank you so much. Vice Dean, Faculty Engineering and Informatics, Dr. Bayu. Thank you so much. Ladies and gentlemen, respect college lecturers and dear students from UPRIS. It is a great pleasure to welcome you all to this special guest lecture. Today we are deeply honored to have all of you, especially to Dr. Bonsale, a distinguished researcher from one of Europe's leading university. It means that known globally for his excellency in science and innovation. Thank you for your coming, Dr. Bonsale. His visit today reflects a shared commitment to knowledge, collaboration, and academic excellency. I think this is very important for us to improve this college. On behalf of UPRIS, I express my warm welcome and express appreciation to everyone joining this meaningful event. Thank you for Dr. Yoga to drive all of them come to UPRIS. Terima kasih Pak Yoga, tentunya sudah banyak waktu yang dikeluarkan. The focus of today's lecture is an essential and timely topic: uncertainty, quantification, mitigation, propagation, and decision making. In science, engineering, and daily life, uncertainty is something we constantly face. It is not a flaw or limitation, but a fundamental aspect of reality. Uncertainty shapes how we interpret data, predict outcomes, and make responsible decisions. everybody, ladies and gentlemen. Quantification help us measure and express uncertainty in data and models. Mitigation focuses on reducing in its impact through robust design and control. Propagation explores how uncertainty moves through complex system, and then decision making integrated all these elements, ensuring that actions are based on sound reasoning, even when information is incomplete. By learning to manage uncertainty, we build resiliency, improve accuracy, and enhance our ability to innovate responsibility. Uncertainty should not discover us. It should inspire curiosity and creativity. Every great discovery began with question, exploration, and the courage to face the unknown. By understanding uncertainty more deeply, we strengthen the foundation of science, refine our analytical thinking, and enhance our decision making in complex situations. So, on behalf of UBRIS, I would like to thank Dr. Syed Bensali for sharing his expertise and this insight for this us. We are confident this lecture will broaden our understanding and inspire future collaboration. Let us begin this lecture with curiosity, passion, and an open mind. Once again, thank you so much for you all come to UBRIS. Terima kasih Pak Dr. Yoga sudah drive them to UBRIS. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you so much. Next, we will proceed with the token appreciation as a symbol of goodwill and mutual respect between Universitas Persatuan Guru Republik Indonesia Semarang and Fine Forces Delegation. First, we would like to invite all the delegation of Fine Forces, Prof. Yan, Dr. Monica, Dr. Satya, Dr. Rajat, Profesor Alcina, Profesor Rui, Profesor John, please come forward. Now we invite Associate Professor Dr. Supandi SSI MSI for giving a souvenir on behalf of Universitas Persatuan Guru Republik Indonesia Semarang.
Apa guys? Masih sarung, Cok. Masih sarung.
Okay, thank you so much, Dr. Supandi. Now we invite Dr. Nur Hidayat for giving a souvenir on behalf of Universitas Persatuan Guru Republik Indonesia, Semarang. Thank you so much. We will continue with having the group photo session with the Fine Forces delegation. Okay, with all the audience, perhaps, for all audience, please stand up and we face there with the background of the audience. Okay, thank you so much. You may sit.
We brought some little tokens ourselves from Belgium that we would like to offer to our hosts. We could not bring that much, we are overloaded. That's my colleague already. I would appreciate an extra slide in case we can move it out in the next. But having said this,
Okay.
this is the one and only tour guide.
Dr. Nur Hidayat, please.
You can fight for it. I will get this to the team. You are the vice keep track of the agenda of Mr. Lee. The agenda is 60 years old. So you can book already the dates that we hope to visit you next year. And last but not least, if you ever would consider coming to Belgium, it is recommended to visit you. I will give you this. Most welcome. Thank you so much for having us.
Taking a picture for a while. Trofian, yes. Okay, thank you so much, Prof. Yan. Ladies and gentlemen, this concludes our opening program for this afternoon. On behalf of the organizing committee, I sincerely thanks to all guests for your presence and participation. Once again, we sincerely thanks to Fine Forces delegation for visiting our beloved university. May this visit mark the beginning of a long-term academic collaboration and friendship. After this, we will proceed with breakout session. Some of our distinguished guests will stay in this room with Dr. Satya, and while others will be escorted to the Senate room for further discussion. So our team will assist you in moving to the appropriate location. So the next session I will give to our beautiful moderator, Madam Anggi. So once again, thank you so much and have a productive and enjoyable session. Wassalamualaikum warahmatullahi wabarakatuh.
Aduh, mic-nya aku pakai yang mana? Moderator mic. Pakai ini aja. Oh, gitu. Iya. Ini ya. Okay. Okay. Okay, can I start now? Okay. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera bagi kita semua. Yang terhormat Bapak Kepala KUI Dr. Nur Hidayat sudah meninggalkan tempat. Kemudian Dekan FTI Dr. Ibnu Toto Husodo dan yang mewakili Pak Bayu. Kemudian Dekan MIPATI Pak Spandi yang mewakili Pak Yoga tadi. PhD Project Coordinator Indonesian Fine Force. Kemudian and all delegates European Union Fine Force. And also our distinguished guest lecturer Dr. Satyajit Bonsale from KU Leuven, Belgium. Serta Bapak Ibu dosen dan seluruh peserta international guest lecture yang berbahagia yang hadir secara langsung di GP lantai 2 Universitas PGRI Semarang maupun yang bergabung melalui Zoom meeting dan YouTube live. Selamat datang di kuliah tamu internasional dengan tema yang sangat relevan dengan perkembangan sains dan industri modern, yaitu uncertainty, quantification, mitigation, propagation, and decision making. Saya, Dr. Putri Anggi Permata Suwandi dari Universitas PGRI Semarang akan memandu jalannya diskusi selama 60 menit ke depan. Izinkan saya memperkenalkan secara singkat narasumber kita. Beliau, ya. Beliau adalah narasumber kita, Dr. Satyajit Bonsale, seorang pakar dan doktor asisten di bidang Chemical and Biochemical Process, Technology and Control Biotech dari KU Leuven, Belgia. Beliau menempuh pendidikan Bachelor of Technology di Teknik Kimia di Dr. Baba Sahib Ambedkar Technological University India. Kemudian beliau juga mengambil pendidikan di Master of Science dan PhD program di Teknik Kimia KU Leuven, Belgia. Beliau memiliki keahlian dalam permodelan, optimasi, dan kontrol sistem bioproses, serta aplikasinya dalam bidang farmasi. Okay, without further delay, please join me welcoming Dr. Satyajit Bonsale. We gladly return the floor over to you.
Terima kasih.
Yeah, for the next 1 hour. Okay, the floor is yours.
Selamat siang. Before I start, as the Dean said as well, I will talk on uncertainty, which is everywhere. Before I start my talk, I want some help from you guys. Right? I'm here for now almost 1 week, but I'm staying longer. I'm staying for a holiday as well. And I'll go to Yogyakarta on Monday. I have my flight next week, Saturday, on 18th of October at 1 in the morning from Jakarta. And I want to travel from Yogyakarta to Jakarta on Friday. And I found some flights. That's the 4 options I have. Which of these flights would you suggest me take? I think I have to go through immigration, security, and I don't know what, baggage transfer in Jakarta, so I need some time there. So which of these 4 flights would you recommend that I take? Anyone? It's not that deep. The question is, I want to go to Jakarta, of course, and I have to fly from Yogyakarta. I found these 4 flights. Which of these flights would you recommend that I take? 1 or 2? Why do you say 1 or 2? But keep in mind, I need like 2.5, 3 hours to, but I have to make sure I go through the security and the immigration and all of that stuff, right? Anyways, but based on that, you can recommend. So for me personally, if you ask me, I would probably go for flight number 2. Right, because I like to have some time so that I am sure that if I have a delay in the flight, I am on time. Right, so how do we make this decision? How do we choose to make these decisions? Well, first thing we said is like, okay, let's look at each of these flights, at what time they arrive, and slightly build a small model, right? So I see that, okay, the red line here is the arrival time as mentioned by the airline company. Right, so the airline company says the flight arrives at 10:05. We have these websites, Flight Aware, Flight Radar, where I can see what happens in the past, how the flights have arrived in time or not in time. If I check yesterday, the flight arrived more or less on time. If I check one more day, that flight was delayed by almost 10 minutes. Right, so you see a flight here, a flight here. If I check more dates, if I start going back in time, I can see how my flight has arrived and how much delay my flight has had. So it seems the flight can be delayed by 20 minutes or even more. Now that scares me because, again, as I said, I have to make sure I go through immigration and stuff. If the flight is delayed longer, I might miss my flight to go to Belgium. I don't want to do that. So I will try to collect as much data as I have, and based on that, I can make what we call a histogram. And it just shows me the probability at which my flight arrives. So, as you can see, there is a high chance that my flight arrives on time. On average, let's say the flight has maybe 5 minutes of delay. That's not so bad. But there is also a very high chance that my flight is quite late, and that might give me a bit of stress to catch my next flight. Right, so based on that, I think I would rate the first flight as high risk. Because I'm a bit scared, I would like to be on time and not miss my next flight. If I do the same thing again, I can do it for the second flight. It leaves at 7, arrives at 8:30. I can go back, look at the arrival times, do the same exercise, and I might say, okay, this one is a bit low risk. I had 2 more flights. They arrive very, very early in time. So I would call them conservative, so very, very low risk. And the other one, I am there in the morning, so I will have to just sleep at the airport and do nothing. So it's extremely low risk. Right, and based on that, based on my preference, I am a person who likes to take low risk. So I would probably choose the flight number 2. That's the thought process I had in going from the 4 options I had to make a decision based on what risk I would like to take. Right, so what did we do? The steps we followed. First, we built a model. What is the model? We looked at the arrival times of all the flights. We found the average arrival time, and we said, okay, based on this, I can make a decision. Step 2, we quantified the uncertainty. What is that? Again, we saw flights can be delayed always. So there is a chance, even if you say the flight arrives at 5 past 10, it arrives anywhere between 5 past 10 and 10:30. So I quantified this uncertainty on my arrival time. Once I know this, I use the understanding I have of uncertainty, and I made a decision based on how much risk I want to take. So step 1, I built a model. Step 2, I quantified the uncertainty. Step 3, I made a decision. That's exactly the steps we follow in an engineering workflow. When we try to build some things, or we design equipment, or we design processes, we start with, in a way, a model. The model can be mathematical or a physical. We quantify the uncertainty, and based on that, we make informed decisions. The task I have for today is to hopefully convince you that models are useful, and the entire message of this talk is to say the way we should design or tackle engineering problems is build a good model, with emphasis on good here, quantify and propagate uncertainty, and then make a decision based on information you have from all of this stuff and based on what you as the designer has in mind. That is the gist of my talk. That's what I'll talk about for the next half an hour, 40 minutes or something like that. Right, but essentially the core message of my talk is this: model, uncertainty quantification, and decision under proper information. Right. Before I start my actual talk, I would say if you have any questions or if you feel I'm speaking too fast, you don't understand me, raise your hand, stop me, and ask me a question. Let's keep it a bit informal. It's not going to be a lecture that I keep talking. Right? Okay. So, we saw this example of the flight. In engineering and in modeling, where does uncertainty come from? Uncertainty, as the dean said rightly, is inherent to every process in the world. Every process, everything is quite uncertain. The first sort of uncertainty we have is in the process itself. We call that the process uncertainty, the process variability. I don't know what kind of engineers you are, but I work in a biology lab. So we work a lot with microbial cells. cells are very stochastic, which means that you can grow them in the same conditions and same culture and everything is same, but they grow differently. Why is that? Because life in itself is uncertain and it's a lot of variability involved with life. So the process itself can be quite uncertain. That's the first source of uncertainty. Then we typically try to build a model. A model is nothing but an approximation of reality. I want to simplify what happens in life and I want to put some mathematics on top of it just to use it to predict what's happening. That's a model. But almost every model is wrong because it's just an approximation. Some models are useful and we want to see how useful a model is. So the second set of uncertainty is from the model itself because we are approximating reality to a very small degree of abstraction of mathematics. Lastly, you have uncertainty in the data itself. Right? No data is clean. You will see every time you measure something, you have a lot of noise on the data. Right? And this noise also affects a lot how we model the process. So these three uncertainties, we need to quantify them and then make sure that we make decisions based on an understanding of these uncertainties in the process, the model, and the data itself. We incorporate all of this. If you look at the traditional engineering models, with an ODE style model, we incorporate all these uncertainties directly in the model parameters. I will call these theta. Right? Then, so step one always of this entire process, as I said, if you go back a couple of slides, the step one of the engineering workflow in a way was to build a good model. What is a good model? A good model is an approximation which tries to mimic reality as close as possible with as less errors as possible. So we need to find a way to build this kind of model. In what follows, I'll assume we know the structure. So here I have an example. I have some data. So in the blue crosses is the data I have measured in the lab. It's a bacterial growth curve. So we grow bacteria in the lab. We give it some sugar, some heat, and it grows. And it reaches its maximum growth on the top there. Right? So we want to model how cells grow in the lab. The blue part is my data. Red is the model which we have available, and we will try to use this model to fit to the data. If you look at the model now, do you think it's a good model? I would say no, because the data is looking somewhere, the model looks completely a bit weird. That's not a good model. In engineering, of course, it's not enough to say it doesn't look good. We need to quantify things. We like to have numbers, right? We need to see how bad is it or how good is it. Quantification is what we work on. So how can I quantify now the error between the data and the model? Any ideas? If I take this point, the error between the data and the model essentially is just the difference, straight difference between the point I have and the point on the model I have. So I can just quantify the error. I call it E. E as the difference between the point here and the point here. That's my error. That's the error on just one point. I have, as I made more data collection, I have a lot of data points here. So I need to quantify the errors on all these points. So I just put that together, and I have errors on all these individual points. Now, that is, if I have 10 points, I'll have 10 numbers for errors. That's not good. I want one number which quantifies the error on the entire model. How can I do that? Well, option one, add them all. I can just add these errors together, and I have one number which represents something. The problem, of course, is some of them are negative, some of them are positive, so you might have a weird differencing between those. Solution, quite easy. If you square all the individual errors, a square of a number is always positive. Even if the error is negative, if you square it, it will be positive. If you square it and then add it together, you are guaranteed that you have one number which is positive. That is what we call the sum of squared errors. Right, so the entire error on the model is the sum of the squared distance between the data you have and the model we have. Once we have that, the problem of finding best models or model calibration becomes finding the best model is essentially equivalent to finding the parameters which make this error the smallest. So if I minimize the SSE being the sum of squared errors, the parameters which minimize the sum of squared errors is the best model parameter in this case. Right, so we have now turned this problem from a visual or a qualitative problem into something a bit more mathematical, something a bit more quantitative, and we can now say the best parameters, so in this case theta star, are the parameters given by minimizing the sum of squared errors. This is again just the same, it's a bit of a vector representation. One small thing you see here is this small sigma inverse. That is nothing but the error on the data, right? Sometimes, or most of the times, we can quantify the errors we have on our data. When we make a model, we can tell the algorithms, okay, this data point is better than the other data point, and we can use it to weigh the models. Right, but okay. So, a quick question. If I were to make a plot, on the x-axis, I have the parameter theta. On the y-axis, I have the sum of squared errors, SSE. Let's say we have only one input, one output. How do you think would the plot look like? So on the x-axis, we have the parameter theta. Y-axis, the sum of squared errors. Roughly speaking, we are squaring things. So we have the model appearing here, and we are squaring things. So essentially, it is something like y is equal to theta squared. More or less, which is a parabola, right? So in most cases, a lot of cases, the sum of squared errors as a function of parameter looks like a parabola. What is the least error in this case? At the bottom. At the bottom is the point of the least error. So essentially, when you do the algorithm, your algorithm is supposed to find this model parameter, which represents the value in which you have the lowest possible errors between the data and the model. On the right, you see the same thing. The only difference is now we have two parameters, and we have what we call a contour plot. So instead of a parabola, the shape of this is like a bowl, right? So and each of this ring is a cross-section of the bowl. So if you look at a bowl, from the top, you see a circle. If you take a slice, you'll see one more circle, right? So these are the circles. Each of the circles represents one value of the sum of square errors. And they decrease as you go inside. So inside here is the least, so that's because it's the valley, it's the bowl. If you take the slice at the bottom, it's only 1 point, right? That's the point in the middle. Again, we have very good algorithms which can do it for us. We have softwares and algorithms which we can put in. We can say, okay, here's my data, here's the model, minimize the errors, and give me the parameters values which minimize these errors. And you would end up with something like this. Again, this is data from our lab. Again, growth curve, so you have some cells growing. You start at this point, a lag phase, and you keep measuring every few hours. And that's the data we collect. And we want to fit what we call a Barani-Roberts model. That's what I show in the corner there. It represents the cell growth as a function of time. Right? The parameters I want to estimate are the mu max, the maximum growth rate, that is the maximum or the highest speed with which cells can grow, and n max is the maximum level the cells can grow up to. If I perform this exercise of estimation, so I have the data, the model, I find the error, minimize the error, I come up with these parameter estimates, right? So this is my model, and now I can use this model to make predictions of what happens in time. So if I say, okay, I do not have data at time 20 hours, right? So if with this model, I don't have any data at this time. But because I have a model now, with this model, I can predict what happens at this point. Similarly, I don't have data at time 40 hours, but because I have built a good model, I can predict what happens at 40 hours. Now the question is, how good is the prediction? As I said, we have tried to build a good model, but we also have errors because you can see the data. If you see this here, the data is quite noisy. That's typical with cells. Cells are quite noisy. We measure quite low density, so we have quite noisy data. So how do we ensure, or how do we quantify the uncertainty I have on this model? Well, there are quite some theories. I will not go in detail about how we quantify, but under some assumptions, what we can say is if we follow things right, if we follow the algorithms right, the parameters we estimate typically come from a normal distribution in which the true parameter, the real parameter is the mean, and we can quantify the variance of it. Right? There is what we call a Gauss-Markov theorem, which allows us to quantify this distribution. So we can say that my parameter estimate comes from a normal distribution. That's one way of doing it. The other way is to, no, I'm going back. The other way is to use Bayesian statistics. Again, give me the same thing. I can start from the data and I can estimate the parameters. How does it look like? Well, the way we represent uncertainty on the parameters is by using what we call confidence bounds. If you read some research papers, you will very often see that when people model, they mention confidence bounds. These bounds essentially are the upper and lower bounds on the parameters. So if you see, for instance, this point here, the parameter mu max, the value of the estimate is 0.24, but we know that this parameter is sampled from distribution. It can be as low as 0.17 or it can be as high as 0.3. So the value can lie in between these two ranges. And we are sure with 95% certainty that the value lies between this range. That's what we can say. Of course, the broader this range, the more uncertain the model is. The broader this range, the more wrong our model is. But we need to still quantify it. Same goes with the Bayesian uncertainty. I can compute pure distributions on my model. So again, mu max is around 2.24, but it can fall or it can be sampled of this distribution. With this, we can quantify the uncertainty on the model itself. What do we do next? Well, sometimes the uncertainty on the model is quite high. We would like to reduce it. Right? We would like to make sure that my model is as good as it can get. Not always easy, but we can try. And one way of doing that is to try to mitigate the uncertainty by designing good experiments. Right? I have a bit of maths for you, so please bear with me for the next couple of slides. But as I said, we have the least square problem. That's the sum of squared errors. It looks like a parabola. When we did the models, we quantified our uncertainty with confidence intervals. We said we have the 95% confidence interval. That's this line I draw parallel to the x-axis. Right? So here you can get the confidence bound. So when I estimate my parameter, the real parameter is somewhere here. But because of the error in my data and so on and so forth, what I can estimate is a parameter, and we can guarantee the parameter can lie between this point and this point. Again, as I said, wider this range, the more wrong the model is, the more uncertain the model is. What I would like to do is to try to squeeze the uncertainty so I can make my range as narrow as possible. How do I do that? Well, as you see, I went in this animation. To squeeze this range, I would like to make my parabola as steep as possible. Right? From a wide parabola, I would like to go as narrow as possible. Again, nice, it's qualitative, but we need to quantify it. We need to put this term down in terms of mathematics. What can we say? Well, every point on this curve is j of theta. This point is here j theta hat. This point is j theta hat plus a small difference. Right? So basically, if I say the difference between this point and this point, if that is very big, then my parabola is steeper. Right? Makes sense, right? If it's steeper, you can take the value of the function at these points, and the difference between this point and this point will be quite large. So To mitigate uncertainty, I have to make sure that my parabola becomes steeper. How do I do that? Well, I need to develop a bit into mathematics. Let's go forward. Taylor series, blah, blah. We use this form here, which is called the Fisher information matrix. This term here is called the sensitivity. We have the covariance, again, sensitivity. Let's look at them one by one. Right, so this is called, like I said, the Fisher information matrix. And to maximize, let's say, the information I have, so to make sure that the parabola is as steep as possible, I want to make sure this term is as big as possible, which translates into trying to make the Fisher information matrix as big as possible. Right, so I want to essentially make this I matrix as high as possible. How can I do that? Well, if you look at the equation blindly, this equation has a few things. The equation sums over all the data points n. It has this covariance and the sensitivity. So the way I can improve my I, the way I can increase the I is first, I just have more data. If my n is larger, if I collect more data, I have more information, I can build a better model. As simple as that. Not always easy, because we need people, we need money, we need experiments to get the data. What next? This is the errors on my measurements. So if I because again you see this is inverse, so if I reduce the errors on my experiments, I can increase the information I have. Again, you can do that. We can try to invest in robots or whatnot. But again, it's quite difficult because every measurement, every technique has at least some error. There is no way that you can minimize the error on the experiment completely. We'll have at least some errors on the experiment always. So we can try it, but it's not always possible. What is left is the other two terms, the Y, the sensitivity terms here. In that, we can play with U. U is the input. When we make experiments, we have a factor we can control. If you are growing, let's say, bacteria, I can change temperatures to make them grow faster or slower. In other examples, you'll see, I show we have different input conditions at which I can do experiments. With these experiments, with these inputs, I can try to manipulate this particular term, the mathematical term, to make sure that it becomes as large as possible. Right? And we do that by quantifying the matrix and using some criteria on it, and then using optimization. So we use what we call an optimal experiment design, in which we optimize a criteria based on this Fisher information matrix, and try to make sure that we design experiments which are so good that we get the best information possible from the data we have. I have an example here for you. One of the works we did with my PhD students was in crystallization. Crystallization is quite a complicated technique. Right? It starts with a solution in which you add the material you want to crystallize. You add a lot of it. You start heating it, because we know that as you heat at higher temperatures, the material dissolves more. So at high temperatures, you have high solubility, and then you start cooling down the solution so that the crystals start crystallizing from outside the solution. So everything in crystallization depends a lot on the solubility. Because if we want to control crystallization, we typically in the pharma industry like to have very fine control over the size of the crystals. We would like to ensure that this solubility curve is well characterized. In literature, you can find a curve like this. Again, the equations don't matter. What is important is that we have parameters which are in red. We need to do experiments from which we get the data, and from the data we build a model which looks like that. But I want to find out these 4 or 5 parameters which you see in red. Experimentation in the pharma industry is very expensive. Right? To give you an example, when I was working in Johnson & Johnson, 10 grams of material can cost something like 10,000 euros in early development. That's very expensive. So we would like to minimize the amount of waste we have, so minimize how many experiments we do. And we can do that because we can make a design space based on thermodynamics, decide, okay, I would like to work in this input space, and then do optimal experiment design. Right, so let me skip these things. So, on the left here, you see the design experiments we had initially. We have almost 54 experiments already available, and we built the solvability model based on these 54 experiments. The model performs good, except in this big region. This big blob of red is the region where the model performs the worst. Now, we would like to actually operate in that region because that region is close to the most optimal conditions in terms of profitability. So I want to operate somewhere around this region, but the information I have is quite low. So I would like to make new experiments which guarantees me to give information in that particular region. I do that following the strategy I just mentioned. I do three experiments, so 2 at this point and 1 at this point. If I add that data from these experiments to my modeling cycle, you can see that I have significantly improved the conditions. So again, red is bad, blue is nice. And I have reduced, let's say, it from very, very bright red to something which is at least a bit more yellow. So I've improved the model quite a bit. How much? Well, you see what happens. We have tried this on different compounds. On the red, on the complete right column, you see what happens if I just add experiments randomly. If I don't design experiment, I just choose, I'll do experiment at this point and see what happens. So I do, let's say, 8 random experiments. And here we do these, so you see the plus number, that's the number of experiments I do with a dedicated design of experiments. So if we follow the strategy, almost in every case, the strategy performs 10-15% better than just adding points randomly. Right, so we have now an approach with which we can design experiments in order to ensure that the data we collect is good enough to make good informative models. Great. So now we have a model in which the uncertainty in the parameters is minimized or as low as possible. But of course, it's a model. In a mathematical model, uncertainty propagates from the input all the way to the output. And we want to see how that happens. So again, to take some examples, if you have a very arbitrary model, so you have the parameter theta, and that's the model, a function of theta. Right? If you have the parameter here, that's your output on the y-axis. Because as I said, when we do our estimation, the parameters we estimate are typically distributions. So what we have is a distribution on the parameter space. That distribution translates, of course, onto the function space. So if you have a distribution in theta, we also have a distribution in y. The job of us as engineers is, because we know this distribution, with parameter estimation, we can quantify this distribution. With this, I would like to see how the distribution here looks like. And that's the job of uncertainty propagation. Right, there are a couple of different examples or different methods which we can use to quantify this. The first one is, of course, Monte Carlo. With Monte Carlo, we sample again and again, repeated samples. So we take a parameter, see what happens, and put it on the y-axis. So let's say we start with the first point, we take this point, put it through the model, see what happens. Okay. Then we take a second point, it happens here, put it there. Third point, put it there. And we keep doing this until we can finally build a histogram. And with this, we have a quantified theta, and we can quantify the uncertainty you have on the output space as well. That's nice. The problem is it needs a lot of time and effort. You have to sample a lot. The sampling convergence is quite high, and you need to have so many samples that it becomes quite challenging if you have a difficult model. Some models are easy to solve. Some models are quite difficult to solve. So if you have a model which is very difficult, computationally extensive, this can fail dramatically. So what can I do else? Well, one approach is to linearize. I can approximate my model by a straight line and use a straight line to quantify some uncertainties. And again, that's possible. We have mathematics which can do that. Right, let's not go into the mathematics now, but keep in mind that if you linearize, the approach is quite simple. You just make a straight line in your model, and that's okay. But it works only if the model is not too nonlinear. So if the model is very complicated, if it has lots of bends and twists and curves in its plot, this method fails dramatically, as I'll show you an example later. So what can we do else? Well, we have another approach called sigma points. Sigma points is based on what an unintended transforms or transformation of distributions from A to B. And the way it works is that you take samples, you select what we call sigma points, you take a few of these samples, you propagate those through the function you have, and based on the sigma point and the function evaluations of the sigma points, you do some fancy mathematics. Again, these are just equations, you do some maths, and you can estimate the mean and the variance of this distribution. That works quite well, again, because you need a very few number of evaluations. It works very well on any nonlinear function. The problem is we have to ensure that the distribution which goes in, so the parameter distribution, has to be symmetric and unimodal, so essentially a bit normal, which is okay if we have, again, parameter estimates coming from normal distributions, but typically and more we rely nowadays on Bayesian estimates, and in Bayesian estimates you don't have symmetric unimodal distributions anymore. So this also can fail in this case. What can we do? We have one more approach which we call polynomial chaos, which then works in these cases. So, again, I have an example here. This is what we call a cone mill. Cone mill is a device used in the pharma industry or also in coffee, actually, to grind the coffee. You drop the particles or the material in this sieve. The impeller goes around in circles. It tries to crush the particles. As the particles get crushed, if they become smaller than the size of the sieve, they fall through, and I have a ground material below. Right? The job was to model that, because again, it was in the pharma industry. We're trying to see how modeling can help reduce the waste products there. And we could model that, right? Because what do we know? What we know is what goes inside the mill. We know the distribution of the material going in. We had a laser diffraction machine. We could quantify the distribution of the particles going in. We could quantify what came out of the mill, right? And we could model the sieve. So the sieve was modeled by saying, okay, I have, based on the size of the sieve, so because this delta function is basically the size of the sieve, based on that, I have a function which says, okay, so many % of particles less than delta fall through, and so many % particles stay in the middle. I can make a model. The model looks a bit complicated, but it's quite straightforward. What I have is n. N is a distribution. So I'm trying to model how distribution changes in time. I have what goes in. N in is the particles going in. I have N out, that's the particles going out. Again, that's simple mass balance. Then I have these two functions. The first one is called death function, because again, this is a particle machine where particles break. The death of a particle tells us how a particle of size x breaks into different, at what rate this particle breaks. We know bigger the particle, the easier it breaks. That's something which we know. Smaller particles are more difficult to break. So that's why we have a model which looks like that. This is the particle size. Higher the particle, more the chance of it breaking. Smaller particle, more difficult to break it. The next one is the breakage function, which tells us if one particle breaks, how does it distribute itself? Because one particle can break into 2 pieces, 3 pieces, 10 pieces, 100 pieces. We don't know. What we do is we have a distribution saying if one particle breaks, it has a distribution which it breaks into. And with this, we can simulate how the D50 is the median size of the particles, looks like. So if I now put a powder which going in, that's the input. It should have been a movie, but okay, anyways. So if we know what goes in at this point, based on the model, I can see what is the particle size coming out at the other side of the mill. And that looks something like that. So this is a simulation where if I change the impeller speed from 4,000 to 1,000, I have a small change in the particle size there. To build this model, we had to estimate some parameters. That's these 4. How do we do that? Again, make some experiments, collect data, do the parameter estimation, and now we have a model which we say, okay, we want to use this model. The question was, is the model good? Can I use this model to make decisions? Well, we were not sure because we knew there was something not great with the data. We were not confident about the data we had. So we said, okay, let's see how this model will perform under uncertainty. we quantified the uncertainty we had on the model, on the parameters here. So all these parameters, we could get distributions. And we propagate these distributions using the methods I showed you to the output being D50. Here's an example. The gray band is the uncertainty band. So even if I predict what happens with this black line, so the black line is my model prediction, in reality, the output can lie anywhere in this gray line. You see a very small, big spike in this thing, and that is where the algorithm has failed. Because this is where I use linearization, so the simplest method, but it fails dramatically when it comes to edges and nonlinearities. On the other hand, sigma point works quite well. You have the model output, and the gray zone is the region in which the model should actually be accurate. So my model can predict 200 or 300, we cannot say. So again, this is just quantifying different ways of, let's say, trying to compare different methods. Essentially what we say is that the sigma point method actually performs the best. If you know that the distributions are normal, then sigma points is a method which will perform quite well to quantify the uncertainty. But this is quite important, right? Because if you look at this plot, my model can predict that my output particle size is around, let's say, 200. That's the prediction. But by doing the analysis of uncertainties, I know that actually, even if I predict it's 200, it can lie anywhere between 250 and 100. That's a big range. In the pharma industry, we realized that this was not good enough because we have strict cutoffs. The aim was, here's the material, find me the impeller speeds at which my particle size coming out is less than, say, let's say 200 microns. With this model, it might seem like I have achieved my target, but in reality, there's a high chance I might not. Right, so in the end, we decided to not go ahead with this model itself. Okay, so what we did so far, we tried to make a good model. We tried to minimize uncertainties on the model. Then we took those uncertainties and we put them through the model and saw how uncertainty in the input affects uncertainty in the output. Now it's time to make decisions. Okay, we have a model, we have the uncertainties on it. Now, how can we decide based on the a model which we have? Again, I have an example. I'm sorry, but the example, I come from Belgium. In Belgium, beer is very popular, so the examples we have are related to that. So it's an example on fermentation. So the fermentation of wort into beer. Right, so that's this process over here. Fermentation occurs anaerobically, you heat up the wort, bacteria consume the sugars, convert them into alcohol and other flavor compounds. That's the model we have. Again, you can forget the maths. Let's just look at them one by one, but you don't have to bother the maths. The first one I have is the amount of cells. So that's the number of cells which actually consume the sugar and ferment into alcohol and other good compounds. Then we have the dead cells. We have the sugar in the substrate, in the wort. We have the alcohol value. And we have these two components which give the beer a bad flavor. In Belgium, if the beer tastes bad, no one drinks it. So we, as a company which is making the fermentation, we have to ensure that we have to keep these two products under a particular limit. Right? But yet, we want to ensure that the beer has, let's say, a high enough amount of alcohol in this case. So the question was, we can manipulate this profile by changing, let's say, temperatures. Fermentation is exothermic, so I can control it by giving heat or taking heat away from the reactors. How can I design the best profile which will give me the flavor profile I would like? That's the question to answer. Well, we use optimization, right? So we, again, forget the maths, but what we have is first an objective. The objective in the case you will see was to maximize alcohol content. They're all alcoholics in Belgium. They want to make as high alcohol as possible. But we are still bound by the process, right? So it's maximize the alcohol content subject to the process we have. By changing the temperature, temperature can go high or low. But I cannot go too high. if I go higher than 16 degrees, the yeast dies. So if the yeast dies, there is no fermentation at all. If I go below 6 degrees, it's too cold. The yeast cannot grow quickly. So again, there's no fermentation. So my temperature, I can be only between 6 degrees and 16 degrees. I also want to ensure that the compounds which give a very bad taste are maintained at the level below, let's say, 2 ppm for diacetyl and 1 ppm for acetyl. That's the goal. So I want to maximize alcohol, ensure my temperature does not go beyond 16 or below 6, and that my fermentation byproducts are maintained under a specific level. We have, again, software and algorithms which we can do that. The second thing we need to do also is to ensure that time taken to the fermentation is quite small. Right? I can let my beer ferment for a long time and I'll have high alcohol content, but again, time is money, so I want to ensure that the time taken is also quite low. So I have this conflict between yield, so which means to make as much as I can, and productivity to make as fast as I can. If I want to make the most, I need to spend time. But if I need to make it fast, I need to have something different. So the idea is productivity is the yield over time. So how quickly and how much you can make in the least amount of time. And these two things are typically opposing objectives. If you want to maximize the yield, you will probably need more time. If you want to minimize the time, you will probably lose on the yield. And this kind of behavior, the conflict behavior, we can quantify in what we call a Pareto front. A Pareto front gives you the objectives you have. On one hand, you have one objective completely. So, but if you maximize this objective, you have a worse performing second objective. If you maximize second objective, you have a bad performing first objective. And you get these points on the Pareto front, which are equally optimal, but they are a trade-off between the two objectives you have. So in our case, yield and productivity. We have a software which can do it for us, the optimization. We have a software which you can use if you want, you can use it, which can be used to solve these kind of problems, to give you, let's say, the profiles of temperature and whatnot. So here is the solution to the beer problem. As I said, we had the objective was to maximize the productivity or the yield. So on one side, you see, if I put in the optimization, on one side, I can make as much alcohol as I want. That's 60 is the maximum I can make, but I need 170 hours. That's this point over here. Or I can make the fermentation go as fast as I want, but then I lose the amount of alcohol I make in that case. That's the conflict here. And you see the temperature profile is given here. So essentially it says if you keep the temperature more or less constant at around 14, 15 degrees, you will try to make, let's say, the most amount of alcohol. And that is the profile. So you see in the green diacetyls, red alcohol, and the diacetyls in the blue as well. Now, this is optimization based on the model. But we just discussed that the model itself can be wrong. We have uncertainty in the model. So how much can I trust this? Right, because again, you see the blue curve, the ethyl acetate curve, that really is on the edge of my quality limits. So if my blue curve crosses the dashed straight line, my beer is bad. It will not pass the quality limits. So how much can I trust the model that I operate on the edge like this? Again, we can quantify the uncertainty, propagate it and see. What happens? We have uncertainty on the parameters. I push it through my model and I get something like that. The blue line is what the model predicts. The red lines are the model simulations under uncertainty. So on the left, it's fine. But if you look on the right, I predict that my blue line says, okay, on average, the quality is okay, but there's a high chance, you can see all these red lines which cross the threshold, there's a very high chance that you violate your constraints you have. So even though your model says the product is good, in reality, something here is happening or can happen and you might have a very bad product. What do? I need to take a step back. I need to be a bit more conservative. I have to say, okay, I don't want to operate on the edge. I want to take into account this uncertainty. And based on that, I would like to make an informed decision now. How do I do that? Well, I take into account, let's say, the probabilities. So if you look at this, again, on my output, I have a distribution. I can quantify the probability with which I violate the constraint, and I can put a constraint saying I want to ensure that I don't violate the constraint anymore. Well, you can say I don't want to do it at all. That's the extreme case, right? I want to be extremely sure that I don't violate this constraint at all. That's very conservative. That can give you answers, but maybe not the best ones. Or you can say, okay, sometimes it can fail, but I want to reduce the chance that my production fails. That's probabilistic. And typically we would like to see on a probabilistic level, what can we do? So here we have an approach, again the maths doesn't matter, but we can say with confidence, okay, I have 95% guarantee that I will not exceed these thresholds. And I would have to do that. So again, example here, the black curve you see here was the original one. So when I optimized my process originally, that is the black line you got there. But then I realized that my model is uncertain and I have to ensure that I take this uncertainty account. So I said, okay, you know what? I don't want to completely ignore uncertainty. I want to be 90% sure that my acetate does not go beyond the threshold, which means I have to back up a bit. I need to do a back off. And if I say 90%, then the curve I get is a green curve. So you can already see that in the normal case, I could get a yield of around 60 grams per liter. But the moment I say, oh, I want to be sure that I don't cross thresholds, 90% sure, I have lost a bit of yield. If I say I want to be 95% sure, that's even more strict, right? I want to take even less risk, then of course I lose a bit more per yield. If I say I want to be 97% sure, again, now I'm being very conservative, I will lose even more yield. Right? So there's always this conflict between performing the best, taking the most risk, which will give you the best output, but of course that's the most risky, you can have a lot of things going wrong, or being very, very safe and playing in this region and saying I will take it easy as well. Right, so with that, I want to come back to my first, let's say, slide I had. How do I choose my flights? Well, I had the same ideas. I had to say, okay, my flight can be delayed, I can have baggage problems, whatnot. I can so I can build my model with averages of delayed times. I can quantify the uncertainty on that based on previous data, the flights, how they have arrived. Based on that, I can rank these solutions, because these are all solutions I can take. I can rank these solutions as risky, moderate risky, conservative, very conservative, and based on the user, me, I can decide on how much risk I am willing to take. Right, so what I've done now is try to implement this workflow to make an informed decision. It can be the risky decision or a conservative decision. Right, so if you are very, very scared, you might go in the morning and stay at the airport the entire day. If you like to live on the edge, YOLO, fine, go take this flight as well. But you have now made an informed decision on what is happening. So that's my last slide. If you want to take away anything from this message, is that uncertainty is inherent in all processes. All models are uncertain. We can try to reduce uncertainty, but we cannot remove it. To reduce the uncertainty in the models, we try to make experiments which are as informative as possible using the optimal experiment design. With that, we can quantify uncertainty and then propagate that through our model. And then finally, we can make informed decisions using uncertainty-based optimization tools that we have. A bit of bibliography, if you're interested in the topic, you can read that, but that's the same thing you see on the scanned page. And with that, I would like to thank you, Terima kasih, for listening. I hope I'm on time. It's okay, the time?
Yes, no worries. Okay. Okay, thank you very much, Dr. Satyajit, for the outstanding and insightful and also highly illuminating presentation on how we manage uncertainty from quantification all the way through to the decision making. Bapak, Ibu, rekan-rekan mahasiswa sekalian, kini kita memasuki sesi tanya jawab. kita memiliki waktu sekitar 15 menit untuk melakukan tanya jawab. Saya akan membagi kesempatan bertanya apabila Anda bisa menanyakan langsung di dalam bahasa Inggris atau bahasa Indonesia yang kemudian nanti saya terjemahkan, silahkan. Tapi kalau bisa bahasa Inggris saja langsung. Supaya tidak misinterpretasi. Ya. Oke. Bagi yang peserta offline, bila ada pertanyaan silahkan angkat tangan dan sebutkan nama serta asal institusi atau prodi. Kemudian bila ada yang online, bisa mengirimkan pertanyaan melalui fitur chat di kolom pertanyaan chat. Ya. Silakan. Silakan untuk bertanya. Oke, Pak Ray. Sebentar. In English. In English.
Thank you for the opportunity. My name is Ramadan Aldi, and I'm from informatics or computer science. I have a little question about the models that you have taught to do a good decision making models. But there are many models available from the older model like bias or regression, or we have a more modern model like neural networks or quantum. In your opinion, are the older models is still good to use for now for modeling data compared to the newer model, because the data is increasingly large. It's that's my question. Thank you so much for the opportunity.
Thank you very much. And Dr. Satyajit, I saw that your research is very interesting. And about the uncertainty, sometimes in our research, we are not really think about that it actually can influence your decision. And I'm curious about your software that this one. Can you please explain to us? And I have really specific question about the quantification, because every variable related to uncertainty can it be quantified? And you explain to us about like the bacterial temperature. Of course, they can easily quantify. And how about the other things? Because we are from different field of study, probably not in biology. Thank you very much.
Okay. You can answer first.
The answer from that is we will have to live with both. We cannot say we have a lot of data, and of course, machine learning AI is upcoming. The problem with machine learning and AI is that it's a black box. With a model of machine learning, you cannot understand the process. You can predict something. So if you have an input, you can predict what will happen at that input in the process. Sometimes that's enough. If that's the goal, machine learning models are the way to go. Sometimes you want to understand the process as well. Machine learning doesn't help us understand things, right? So then we need to rely on engineering models which help us there. Also, what happens more and more, we say we have a lot of data, but that's not always true. Because if you want to build an ANN, you know it better than I do, you need a lot of data, which is possible. Let's say if you have sensor analysis, you have temperature sensors, things, but something like cells, right? So in the example I gave with the cells, it is a student who is counting the cells. I cannot make him work 24 hours a day, right? So I have not a lot of data, so I have to make do with what I have and machine learning. So what we do now, more and more, is we call hybrid models. So we have a mechanistic or a physics-based core of the model, and there are some parts of it which we say, okay, this I can plug in a neural network or regression model or logistic regression somewhere there. So we try to combine best of both worlds. I hope that answers your question. And coming back to you, yes, uncertainty is everywhere, right? I give you the example of the bacterial cells, but also it was the case in, let's say, modeling the cone mill. That's where we broke particles. That's even more uncertain because breakage is very uncertain. You know, you break one particle, it can be into 2 or 3 or 10, we don't know. The uncertainty I deal with is in model parameters. So, right, you can measure uncertainty always. So, you can always do that, right? You can do the same experiment, same conditions again and again. And if you measure it 10 times, you have 10 different outputs, more or less. You can quantify that. That's the uncertainty on the data. If you have the model, you can do the parameter estimation, and you can propagate that uncertainty on the data into the model. So, I would say in almost all cases, you can quantify uncertainty in the model parameters. Sometimes it's not easy. It can take quite some computational power, but I think we can. Especially nowadays with big computers and Bayesian approaches, we can quantify it quite well. There's something else as well.
Show us about the software and
Ah, yeah.
things, yes.
Where did it go? Yeah, well, it's a software which we developed quite a while ago to solve problems of optimization. Right, so we have what we call dynamic optimization problems, which have to be solved yeah. So it's basically a wrapper. So you can put your model in there. You can get it run, and that solves the objective, and it will give you an output. Let's say something like this. It tells you, okay, this is the point of front you have, and you can make decisions based on it. But before you get to that stage, you have the problem ready. Like the model has to be ready.
Okay, next question. Is there any? From the student? Okay. Okay, sir, I have one question. In our countries, it's a little bit difficult to have the high quality data for the models like this. Yeah. So, what do you think about what is the most what is it strategy? How to
I always say
data
data is
limitation.
data.
Yeah.
There is no, for me, the answer is always data is data. There is no bad data. You can say it's bad quality compared to something which is better, but the bad quality data is still data. So if you don't have anything, that is still good enough. So we can make models, and that's again where uncertainty comes in. If the data quality is not that high, you will have an uncertain model. But as long as you know that, you can make decisions based on the model, keeping in mind that, okay, the data I built my model based on was a bit of low quality, which means my model will be quite uncertain. So I have to, whatever decisions I make based on the model, I have to be a bit careful. Models can't solve it all. We have to also use our physical understanding of the process to then make a decision informed by the models. Right, so data is data, whatever it is. If you have data, use it. That's what I would say.
So whatever the result, data is data. And
Yeah, well, what is the result? Data is data, make the model, and then use the understanding you have on the data to assess the quality of the model and make informed choice. The emphasis is on informed decision. If you know that the data is not good, you have to keep that into mind when you make decision based on the model.
Okay.
That's what, yeah.
Okay, thank you. Okay, is there any question from the student, please? Maybe from the online, is there any question? No? Okay, so baik, sepertinya kita akhiri dulu untuk sesi tanya jawab kali ini. Kami mungkin kalau ada yang masih ingin bertanya tapi terkendala bahasa atau masih takut, ya mungkin next time bisa digunakan Google Translate-nya. Oke. Oke, izinkan saya untuk menyimpulkan sedikit dari diskusi hari ini. Inti dari pemaparan dari Dr. Satyajit adalah bahwa ketidakpastian bukanlah sesuatu yang harus dihindari, tetapi harus dikelola secara sistematis melalui kuantifikasi, mitigasi, dan propagasi yang baik. Sehingga nanti prosesnya ini bisa menghasilkan keputusan yang cukup akurat. Oke, thank you, Dr. Satyajit, for sharing. Mbak Nadia. Oke, thank you, and then you can sit down here. Okay.
Kita yang sesuatu iya. Dia boleh. Banget. Sampai kita boni.
Oke, sekian dari acara hari ini. Terima kasih untuk kehadiran mahasiswa sekalian. Semoga ilmunya yang diberikan bisa bermanfaat bagi kita semua. Oke, selamat sore dan selamat beraktivitas. Tapi sebelumnya kita akan melakukan sesi foto bersama ya. Oke, can we take a picture first? Ya. Sopo sih main moto? Fotoin.
Walking.
Chemical engineering.
Jumit piye? Aku nelpon Bu Mega kebiasaan soalnya sih. Tapi iki nelpon iki nih, Ndak. Ya kuwi maksud juga ben saya ngedeng Bu. Masalahnya kan mau pakai kantong sendiri. Kalau kamu kirim ke sini bisa. Angin saya Oh yes, yes. Thank you, sir. Walking in the house. Itu nak. Iya. Dua lagi. Tuh. Ini zoomnya langsung tim Afin aja zoomnya.
Ya, cuma hari ini
Off ya, Ge?
ya, Ustaz.
Orang zoom kan ya, gitu pe dul Tapi kok dibikin pointernya nih di. Wes mau pointernya. Langsung nah gitu berarti kalau mana YouTube kan di perono para tapi yang bilang tapi bapak aku yang rawani loh. Excuse me, sir. You can share your material. Can you share? Yes, I'm walking. Ya kalau tak aja sing marwah ini ya. Ben shop I want to break free. I want to break. I want to money. Iya. Iya betul. Mas, ini udah nih tapi habis capek ya. Saya huge shit. Ya, off, video off. Terus kita close langsung.